Have you ever wondered why time only moves forward and never backward? It's a question that has baffled the greatest minds in history. Time, as we perceive it, is a one-way street. But why is that? Let's delve into the realm of physics. The fundamental laws of physics, from Newton's laws of motion to Einstein's theory of relativity, don't really care whether time is moving forward or backward. They hold true in either direction. This symmetry between the past and the future is a cornerstone of our understanding of the universe. But here's where it gets interesting. There's one concept that seems to break this symmetry, and that's entropy. Entropy is a measure of disorder or randomness, and it's the one thing that gives a direction to time, always increasing as we move from the past to the future. So if entropy is the key, what makes it so special? Let's explore this puzzle in the next scene. Entropy, a term often heard in the realm of science, but what does it really mean? Let's dive in. Picture this. You have a neatly stacked deck of cards. Each suit is together, and each card is in order. You shuffle them. What happens? The order is lost, replaced by randomness. Similarly, entropy is a measure of disorder or randomness in a system. It's a concept that's as fundamental to our universe as gravity, but let's simplify it further. Imagine dropping a glass on the floor. It shatters into a million pieces. Why doesn't it spontaneously reassemble itself? Well, that's entropy at work. There are far more ways for the glass to be in a shattered, disordered state than a whole, ordered one. So the likelihood of it spontaneously unbreaking is ridiculously small. Now let's bring time into the equation. If you observe a movie of a glass shattering played in reverse, it would seem odd, wouldn't it? That's because our world has a preferred direction of time, from the past through the present and into the future. We call this the arrow of time, and it's determined by the increase of entropy. In other words, as time moves forward, entropy increases. The universe, like our shuffled deck of cards or broken glass, tends towards disorder. This is a fundamental law of nature, known as the second law of thermodynamics. It's why you can remember yesterday but not tomorrow. But here's a mind-bender. What if we told you that the arrow of time isn't universal? What if we told you that there's a place where this law doesn't apply? It's a realm that defies our everyday logic, where time may not have a preferred direction. Stay tuned as we dive into the fascinating world of quantum mechanics next. Welcome to the quantum realm, where the normal rules of physics take a back seat. This is a world that defies our everyday understanding, a world where particles can be in multiple states at once until observed. It's like being at two places at the same time, until someone catches you in the act. In the quantum world, time doesn't march forward in a set direction. It's more of a waltz, really, moving forward and backward, with particles potentially influencing their past selves. This concept, known as quantum superposition, is a bit like having your cake and eating it too. It's all a little mind-bending, isn't it? But this quantum weirdness is not just theoretical. It's the basis of technologies we use every day, from lasers to computer chips. So, the quantum world is not just strange, it's incredibly useful. So, is time travel possible in the quantum realm? Well, we'll dive into that in our next scene. Time travel, a concept we've often seen in science fiction, but could it be a reality? In the quantum world, it's not as far-fetched as it may seem. Scientists have theorized that quantum particles can behave in ways that seem to defy our understanding of time. Some suggest quantum particles can exist in a superposition of states, essentially being in two places at once, or even interact with their past selves. However, let's not get ahead of ourselves and start drafting blueprints for our time machines just yet. These quantum phenomena occur at such a microscopic scale that they can't be directly applied to the macroscopic world we inhabit. Furthermore, even if we could somehow harness these quantum quirks, the rules of entropy and the arrow of time still dictate that we can't reverse the flow of time as a whole. While time travel remains a fascinating concept, for now, we're bound by the arrow of time, always moving forward.